Very much. So this will be a surprise. The talk is based on two joint works. One is with Buczyński, Januszkiewicz, and Jelisiejew, and the other one with Chris Miller from UC Berkeley. And I will introduce topics that are completely not related to the previous talk. So there are no connections, and that's just a different work. Let us start a long time ago, when a concept of manifold was just emerging, and it was not clear what should be the correct definition of a variety or of a manifold. Namely, should the variety be embedded or abstract? And then there was a theorem due to Bertini and later Whitney, now known as Whitney embedding theorem, that if we consider a topological real manifold of dimension m, it can always be embedded in an affine space of dimension 2m plus 1, and even 2m. People don't know, but there is a long, many years have passed from this to this. Whitney was thinking about good embeddings, and in some sense this theorem is optimal. That is, there exist infinitely many m's, which are powers of 2, and there exist manifolds such that they cannot be embedded in 2m minus 1. How do you do this? Well, you compute certain Stiefel-Whitney classes, and sorry, here these are just like Whitney classes in this example, and by certain non-vanishings you can deduce the fact that embeddings cannot exist. There are still a lot of open problems here, meaning what happens for an arbitrary m, what happens for an arbitrary manifold, what's the best embedding, but this is the classical setting that I wanted to recall, now almost 100 years old.
Bertini is we know that, right?
Yes. That's because that's before, like, so we will see that this 2m plus 1 is in some sense very easy, and we will discuss it in a second. Mm-hmm. But then the question is how well a manifold can be embedded, and what does it mean to embed well a manifold? Let us think, what is an embedding? And the main property of an embedding is that if we take 2 points, it's a map that does not glue points. That's the main property of the embedding. But we can rephrase it that if we take any 2 points, their image will not span a point, but it will span a line as an affine subspace. And this is the property that Borsuk observed in the 50s. In fact, maybe it was even a little earlier. Namely, he defined k-regular maps. And a map, an embedding of X in Rn is called k-regular if the images of any k points span a k minus 1 dimensional affine space. So you can either work with linearly k-regular and then they are linearly independent, or k-regular and they just span an affine space of maximal dimension. And the question is, how well can you do this? The same question that Whitney asks. So what's the smallest possible n? So note that for k equal 2, this is just the definition of an embedding. Yes? So for k equal 2, a 2 regular map is just an embedding. But a higher regularity is something much more complicated. So this is the first motivation. How well can we embed, which k-regular maps can we find?
In algebra, that is k-ample.
Sorry?
That is k-ample in algebra.
K-ample in k-variample. K-variample is k-regular. I would have to recall exactly how it went.
I don't know. Maybe similarly defined like this.
K-variample.
Yeah.
I have to recall. Sorry. This definition is much older than any classical algebraic geometry notions we have now. Now we change the topic completely. From topology, we go to interpolation theory. So what is interpolation theory? I'm not an expert in interpolation theory at all, but what does it mean to interpolate? It means that we know some values, and we want to know the values of the function everywhere. Yes? So in other words, we are looking for a function that takes a prescribed values at the prescribed points. But what kind of a function? Well, we can always take a function that is, let's say, 0 everywhere, apart from the fixed points, where it takes the particular values. And then someone says, well, maybe we should look at continuous functions, or infinitely differentiable functions, or low-degree polynomials, or something like this. And in particular, we would like to have a small space of functions that would still allow interpolation theory. And this motivates a definition, also a very old one by Haar and Chebyshev, that on a vector space V, a family of continuous functions is called k-interpolating if no matter which k points we choose, and no matter which values we assign to them, there exists a function that takes exactly those values at exactly those points. Yeah, so that's a k-interpolating family of functions. And what's the aim here? We would like V to be of small dimension. Well, of course, if you take, for example, some huge dimension, this is possible, but then maybe your interpolating functions are not so nice. So here the problem is to find V of as small dimension as possible. So we have these two completely different words. Topology, we are looking for good embeddings. And interpolation theory, we are looking for families of functions that allow interpolation. And it turns out that this is the same. It's absolutely the same problem. That is, an n-dimensional k-interpolating space for x exists, even only if there exists a k-regular map from x to Rn. And I'm not even calling it a theorem, because a proof takes like 10 seconds if you think about it. You just take, if you have a k-interpolating space, you just take a basis of this space and use it as an embedding. And if you have a k-regular map, you just compose it with the linear functions from Rn. And it's very easy to see. So in both cases, the problem is the same. Looking for small dimensional k-interpolating spaces and looking for an ambient space of a k-regular map with n as small as possible. And as I said, I mean, these problems are very natural and very old, over 60 years. So they attracted attention of many people, but mostly not algebraic geometers, but topologists and other mathematicians, also in applied mathematics. Very recently, there is work of Ziegler, Blagojevich, Cohen. These are more recent results. And let me tell you, what do we know? What do we know about this n? So maybe before what we know, let me tell you what are the most interesting cases and questions that we would like to consider. So embedding an affine space is trivial. The best embedding of an affine space is just an identity map. But it turns out that for k-regular maps, the problem is highly non-trivial. So if you want to have a map from a 5-dimensional vector space, such that the image of any 10 points will be linearly independent, it's a highly non-trivial question to answer what's the minimal ambient dimension. And in some sense, it's maybe the most interesting, because when you are doing interpolation theory, your underlying manifold is usually just the affine space. Here, I did not say anything about the field. Originally, because it was like in the 50s, so people were mostly interested in real vector spaces. But you can ask those questions over complex numbers, and this is sort of the modern approach. Now more and more people are looking over the complex field. So how this thing looks like, how if you look at the history of this problem, well, most of the theorems are of the type you cannot find a k-regular map from AM if big N is smaller than something, and then people are improving this something over the last 60 years, and current world record holders are Blagojevich, Cohen, Luke, and Ziegler. Here is a theorem, but to be honest, I shouldn't call it a theorem, because very, very recently, one of the theorems, so their paper is correct, but it turns out that one of the papers they use the theorems from is probably not correct. So right now we are not sure if this still holds, but it gives at least an estimate, and I think the authors are writing an erratum how to save these results without the theorem that they were using, and that might be false. Well, as I told you, the theorems usually tell you that the k-regular map does not exist when n is small. And here the n is smaller than the product of m and k. And there is this alpha of k. So what is this alpha of k? It's the number of ones in the binary expansion of k. A very, very strange value, at least for an algebraic geometer. But think about it as 1. I mean, if something, for example, is a power of 2, then it has just one in an expansion of k, and then we are getting m times k minus 1. Okay, so this is the real result, and the complex one is almost the same. It's almost the same, and in particular, this is for sure a correct result, so this part does not base on the problematic theorem, that when k is a prime number, you are also getting n less than m times k minus 1. So, when n is smaller than this number, there is no k-regular map. Now, what about the other way around? So as I told you, over the last 60 years, these people were improving and improving these bounds, and they basically reached, at least for some special values like k prime or a power of 2, that m times k minus 1 is optimal. But it turns out that we have almost no existential results. That is, a construction of k-regular map is very hard. And from the point of view of applications, if you are looking for those interpolating spaces, well, maybe the result that there does not exist an interpolating space is less interesting for you than a construction of an interpolating space. So far, the constructions we have, first of all, are quite far from optimal, and second of all, they are for very, very particular numbers. So this is one paper. A whole paper is about this theorem that such a map is 4 regular. Yes, so 4 regular. Okay, so here we have to multiply 3 times 3, we have to add 1. So the optimal bound that we expect from these theorems would be 10. So we know that there is no map for n smaller than 9, but here we have to go to a 12-dimensional space, and it's whole paper just from R3 to R12. You have to use very special properties of these polynomials. I mean, these are not just random coefficients, and I will say a few words why these are not random coefficients. And then you have to prove that this is 4 regular map. And the question is, can you do the same to R11 or maybe to R10, or maybe you cannot do it? These are open problems. Well, I will say which are still open and which are not open anymore. Okay, so that's basically the state of the art, and I'm an algebraic geometer, just as Jarek and Joachim. Tadeusz is a geometric group theorist, whatever that means, and we wanted to do something with this problem. So what can we do? I mean, these are problems in topology. Well, maybe this previous one looked a little algebraic, but very, very particular. So what do? We decided to use the power of the ring. And not just any ring, but the Gorenstein local ring. So before saying how the Gorenstein local ring appears here, let us start in a place we all know. So how would you construct a k-regular map from a projective or an affine space? That's the question to the audience. Yeah, so you want a map from a projective space, let's say that is 10 regular. So no matter which 10 points you take, the image will span an affine or a projective space of dimension 9. How would you do that? Maybe let's start with 2 points, with 3 points. So how can you make any 3 points linearly independent? So if you take any 3 points, you don't want the image to lie on a line. How to do this? Maybe start with a curve. Yes. So we start with a line, and how would you put this line in some space so that no 3 points lie on a line? There is a construction, I think it either goes back to Hilbert or Grothendieck, but it's very easy. And it appeared already during my last talk, so maybe that's the only connection to my last talk. Namely, the Veronese has this property. If you take the k minus first Veronese, that is, here I work affinely, so I take all polynomials of degree at most k minus 1. This provides an example of a k-regular map. So if you take the Veronese re-embedding. In fact, this is the idea that Grothendieck used to construct Hilbert schemes. Okay, but this would give the ambient dimension m plus k minus m choose m. That's the ambient space of the Veronese embedding. So I mean, we cannot present such a result because topologists would laugh at us. So we need to do something better. That is a k-regular map, but the big N is much bigger than we expect. Remember, our final aim is something about m times k or something like that. So let us go back to Whitney. He was a very good mathematician, so let's think how he managed to prove his embedding theorem. So why it was easy to embed a variety in the ambient space of dimension 2m plus 1? Do you know? What is this number, 2m plus 1? If you have an m-dimensional variety, why can you embed it in the space of dimension 2m plus 1? Say you can embed it anywhere. So that's our Veronese. It's already k-regular, and now we so imagine a manifold in some huge space, but it's only m-dimensional. How can you go down with dimension of the ambient space? You project. That's the natural thing, but you have to be careful. Yes, you cannot just take any projection. Yes, sorry. Yes, but so how can you do it? What have you do? Yes. So when you will be projecting, you need to you need to, so you have to choose a point that is the center of projection, and you do not want to glue points. So you do not want to have a line that intersects your variety at 2 points. So in other words, you can take the secant variety, and what's the maximal dimension of the secant variety? 2m plus 1. Yeah, you have to choose 2 points, and 1 is for the line. So as long as your ambient space is of dimension bigger than 2m plus 1, you can always choose a point outside of the secant variety, and you can project. Perfect. So that's the dimension of the secant variety, and now we have something more complicated. So embeddings, these were 2 regular maps, and now we are looking for k regular maps. So the role of the secant variety will be played by the kth secant variety. Yes, we have our Veronese map, which I already told you that has a property that if we take any k points on the Veronese, the linear span is of maximal dimension. So what do we want to avoid right now? We want to project, we want to follow Whitney's idea, but when we will be projecting, we don't want this space of dimension k minus 1 to become of lower dimension. But when a space changes the dimension under projection, even only if the point belongs to the span of this ambient space. So in other words, we will want to avoid the secant variety. Okay. That's already much better. So as long as we can find a point outside of the Veronese, we can project. And this gives us the dimension of the secant variety. This is mk plus k minus 1. And this is already not bad. So remember, they had something like a times k minus 1, so that's already not bad. But of course, this was known for years. I mean, people study this. These are great mathematicians, Vasiliev and so on. I mean, such an easy idea. For sure, they knew it, and indeed they did. So we need something better. We need something better. And how can we do something better? And it seems that we cannot do anything better because well, we need to avoid all of those secants, and when the dimension of the ambient space is already equal to the dimension of the secant, I mean, we cannot project. So what could we do? Well, one thing is that we can hope that the secant is of lower dimension, that it's not of dimension mk plus k minus 1, but maybe it's of lower dimension, and then we can project farther. The bad news is that the secant of Veronese, well, maybe it's a good news, that the dimensions are known. This is a very famous Alexander Hirschowitz theorem. But the bad news is that this theorem tells you that almost always the secant variety is of expected maximal dimension. That is mk plus k minus 1. So this hope dies quite fast. This does not lead to new k-regular maps because the secants are usually non-degenerate. What else can you do? Well, here, the property that you want when you will have these k points is that you do not want to be in the span in the linear span of those points, but you still may be on the secant variety. There is nothing wrong with that because the secant variety needs a closure. So not every point on the secant variety is in a linear span. And if you will be outside of all the linear spans, you are fine. You are fine. So that's an idea. Try to understand this closure in the definition of a secant variety and try to pick points, special projections. By the way, already Alexander Hirschowitz's theorem tells you, because how could you try to construct k-regular maps? One of the ideas is to take random polynomials. Yes, it seems that random polynomials should make the space very unlinear in the big ambient dimension. But Alexander Hirschowitz tells you, no, this is not true, because generic polynomials correspond to generic projections of the Veronese. And the generic projection will intersect the secant variety, but it will also intersect the open part of the secant variety. That is, it will intersect some linear span. So if you take generic polynomials, it's not a good idea. You need to find very, very special polynomials. Or in other words, very, very special projections of the Veronese to obtain k-regular maps. You need to find points that belong to the secant variety, but do not belong to any secant, any k-secant. Okay, what else can we do? Well, we can go back to the 50s and say, these people want real answers, and intersection theory does not work very well over the reals. That is, you can find a big real subspace disjoint from a high-dimensional real variety. This is, in fact, a path we have not tried at all, and maybe one can indeed use something here. And the last point is that intersection theory fails in two cases. One, when the field is not algebraically closed, but the other is that when your variety is not complete. So maybe you can find your center of projection intersecting the secant variety at infinity. So in other words, your center of projection, when you will just look at the affine part, it will be disjoint from the secant variety, but it will sort of meet in the infinity, in the projective space. And astonishingly, this last point 4, that sounds completely crazy, because we are looking at an open set, turned out to be the most promising. But we need to forget one thing, that we are algebraic geometers, and we need to think like a topologist. So what's the difference between topologists and algebraic geometers? Well, topologists have balls, and big balls, small balls, whole space, they don't care, they don't distinguish between these objects. So our whole affine space for them is just as good as a small ball. So maybe instead of avoiding all the secants, let us try to avoid secants from a small neighborhood. Yeah? If we can find a point that avoids secant lines of a small ball, we are good, because we can still construct a k-regular map, because we can first find a non-algebraic map that makes a homeomorphism of an affine space and a small ball, and then we can compose it with an algebraic map, the Veronese and the projection. Yes? So that's, if there are any questions, please ask. Yeah, that's the idea. That's the idea. So the idea is like to make this with the ball, which also is inside an AN, then take a Veronese. Yeah, so we are getting some variety, and the secant variety is huge, but the image of a ball is small, and if we look at secants of the ball, this is not an algebraic variety, it's not anything. It's a set. But if we can find points or subspaces disjoint with these secants, we can make a projection from that subspace, and all of the subspaces will still be of the correct dimension. Okay, so the idea to take a ball is a good one, but of course, if this ball is too big, then we are not gaining a lot. So let me make a picture. Yeah, so we take a ball, and we take all the secant lines inside the ball, all of them. Yeah, you see what we get. We will get something like that. Yeah. Okay. Then we take a smaller and smaller and smaller ball. Yeah. So we are getting smaller and smaller and smaller sets. And what do we get? So now it's time for biology. This is a cactus. And cactus have spines. And they also have, you see the spines, they are coming from this thing that is a part of a stem, and this is called an areole. And when it comes to secant varieties, a lot of objects are named after botany, because people think about the cactus, about the stem of the cactus as the secant variety, and then the spines are linear spans of non-smoothable schemes. There is a cactus variety, but then there is something that is more local. It's not here a spine, it's a part of a stem. It's much smaller than the spine, and it's called the areole. So now a mathematical definition, not a botanical definition of an areole. Let us take a complex projective variety and a point. The idea behind the areole is that this is a punctual variant of a secant variety. So we want to define a secant variety at a point. Not a secant variety of a variety, but a secant variety of a point. And algebraic geometry allows us to do it, because we can work with schemes. So what is a secant variety? Well, the secant variety is made of linear spans of k points. But what is k points on a variety? It's a smooth scheme. Yeah? The only smooth scheme of length k, these are k distinct points. But now we take a smoothable scheme supported at P. Yeah? So when k is equal to 2, there is only one smoothable local scheme, k of x divided by x squared. There is this citation about relation to botany that this is due to Jarek, that just as beautiful flowers grow out from areole, regularity theorems spring out of properties of the areole variety. This areole, this local variant of a secant variety, will be the key to prove new results in topology on k-regular maps. Yeah, so we should think about it as a local analog of the secant variety. I can also tell you that there are new results that also say that this is not only useful only in topology, but also in computer science with things like fast matrix multiplication. So these areoles also govern some complexity problems. Okay, so let's talk more about these areoles. So secant varieties are parameterized by k distinct points. And distinct points on X, they correspond to an open subset of the smoothable component of the Hilbert scheme. So the Hilbert scheme is a scheme with points corresponding to schemes of a given degree in the variety. There is one component called the smoothable component, where the generic point of a smoothable component corresponds just to distinct points. Okay, of a given fixed length. And And distinct points, these are the only smooth schemes. But Hilbert's scheme is compact. So if you have a component, and if you have points corresponding to distinct points, if this is compact, something must happen when the points come together. Yeah? And you are obtaining schemes. Yeah? You are obtaining schemes that are called smoothable. So in other words, a scheme is smoothable even only if it is in a flat family with a generic fiber equal to k distinct points. Okay, so as we are interested in the punctual version of the secant variety, we take only those subschemes from the smoothable component that are only supported at one point. Yes? So that's a complete analog of the definition of the secant variety. And now comes a very easy theorem. Once you know this definition, proving this theorem, you can do it faster than Gregory proved his theorem last time during the previous talk. That is, it turns out that in order for a small ball to exist with secants disjoint from a given point, you do not have to avoid this strange monster that is the union of all secants in a small ball. You just need to avoid the areoli. The areoli is an algebraic object. Yeah, so an example of an areoli and how this thing works. Let us take the second Veronese of a line. That's a fancy language for a parabola. And let us fix a point. Okay, so we were looking at limits of taking all secant lines over small and smaller balls. Do you see what will be the limit? Yeah, if I take a very, very small ball and I take all secant lines, what will be the limit? The tangent line. Yeah, you are getting like a very, very small thing. So if you take a small ball, what you are getting is basically like something like that, and it goes thinner and thinner, and in the limit you get the tangential variety, the tangent space. The tangent space. And indeed, if you remember the algebraic definition of the tangent space, this is the linear span of all schemes like this. Yeah, you need to embed a scheme like this at this point, and you need to take a linear space. Yeah, so this is the areoli for k equal 2. Yeah, so for k equal 2. It's just the tangent space. But when you are getting more points, this becomes much more complicated. It's not a linear space or anything like that. It's really a variety, and it's a complicated variety. Okay, but now the point is that if you can find a point that avoids the areoli, that is here the tangent space, it means that these points will also avoid all secants in a small analytic neighborhood. Yeah, this is clear. I mean, this point will not intersect these secants. And analytic is really important here because there is no Zariski open neighborhood such that you would avoid all the secant lines. Yeah, because, well, for every point, you would have to get rid of one of those 2 points. That's not Zariski open. Okay. But the theorem is not difficult once you have the definitions and the ideas. Probably just as in Grigory's case, when you write the correct theorem, the proof is easy. Okay, so what's the gain now? The gain is that areoles are much, much smaller than the secant varieties. So instead of avoiding a huge secant variety, we just need to avoid a small areoli. And how can we bound the dimension of the areoli? Well, we have to go back to the Hilbert scheme, and we need to bound the dimension of the local smoothable schemes inside of it. So what's the dimension of the areoli? Well, this is the dimension of the Hilbert scheme. This is the dimension of the punctual Hilbert scheme. And here we have to add k minus 1 because each scheme can span at most a space of dimension k minus 1. So this is the highest possible dimension of the areoli. And this already shows you that such k-regular maps exist. Yeah? So when n is m plus 1 times k minus 1. And this is currently the best known general bound. And here, the only thing that we were bounding is that schemes corresponding to local schemes in a Hilbert scheme form a divisor. Yeah? So it could, I mean, that was very strange for me. So this is again, I mean, we have a Hilbert scheme, and the generic point in the smoothable component corresponds to distinct points. So let's say we are looking at the Hilbert scheme of 5 points in the 3-dimensional space. So the 5 points are represented by the ends of my finger, and as I move in the Hilbert scheme, this point change. Yeah? But when I move in a special way, 2 points crash, and I'm getting a scheme like that, and 3 reduced schemes. So this is a divisor. You can compute it very easily, because you have to choose this point, then this point is characterized by the dimension in the free space, and then there are 3 other points that go loosely around. So there is a divisor of such points. Well, then you can go deeper and you can ask, what are these points? Well, this is a further degeneration, so you expect a divisor in a divisor. So a codimension 2, codimension 3, codimension 4. This is not true. This is not true. So what happens in the Hilbert scheme is that there are divisors that correspond to this. Not points coming one by one, but all points coming together. And this may form a divisor. That's very, very strange. But it happens very rarely. So the areolis tend to have much smaller dimension. And let me tell you in which cases we can prove that the areolis are of smaller dimension. Well, we have to take into account that these punctual Hilbert schemes, bounding them by a divisor is not a good idea. So we do not know much about arbitrary schemes, but fortunately we know much more about Gorenstein schemes. And I'm not going to define Gorenstein schemes here. You probably know this story that Gorenstein said that he never understood the definition of the Gorenstein ring. So let's not present the definition of a Gorenstein ring. Let me just tell you that local Gorenstein rings have got a very nice interpretations as quotients by ideals given by annihilators of polynomials. So if you have a polynomial, you look at derivatives that annihilate it. This is an ideal in the ring of derivatives. And this is even only if for a local Gorenstein ring. And this is called the Macaulay duality. So in particular, this is a very useful tool for classification results. If you want to classify Gorenstein local things, you just have to look at polynomials. The property that is crucial for us is that if you have any scheme R, if you take its linear span, it's a union of the linear spans of Gorenstein subschemes of R. In other words, if you are taking any linear span of a Gorenstein scheme, of any scheme, you do not have to consider that linear span at all if you just consider linear spans of Gorenstein schemes. Yes? So instead of bounding dimension of smoothable punctual schemes, it's enough to look at Gorenstein schemes. Okay. And we have a quite good understanding of local Gorenstein subschemes because there is a work of many people, like there is a book by Jarobino, there are many articles by Kasnati Notari. Hilbert scheme was studied like for over 40 years by many, many great mathematicians. So they give us a lot of tools for free. And that's maybe a little exaggeration. They give us a lot of tools when k is small. So when we do not have too many points. Okay, so to sum up, what can we do to bound the dimension of the areoli, our main task? We have two options. We can either consider smoothable punctual schemes, that's the first one, or we can consider Gorenstein schemes. But there is a problem here, because you may have a smoothable scheme, and you want to take its linear span, and it is covered by linear spans of Gorenstein subschemes, but no one can assure you that these are smoothable. So the second option might be in fact worse if you take all Gorenstein schemes. But again, there is good news. When the ambient space is of dimension at most 3, or if you have at most 14 points, then this second option is better because all Gorenstein schemes are smoothable in this range. So we just need to understand the dimension of local Gorenstein schemes in the punctual Hilbert scheme. Okay, so what's the theorem? The theorem tells us that in that range, my hand trick works. So 5 points coming together is of codimension 4, indeed. It's not a divisor, it's of codimension 4 condition. So this gives us, when k is at most 9 or m is at most 2, there exist k-regular maps from Rm to Rm k minus 1 plus 1 and c. So you see, this is the best possible. This is m times k minus 1. As soon as the paper will be corrected, we will know that this is the best possible bound. So let's compare with the topologists. Over the complex number, this is optimal for k equal 2, 3, 4, 5, 7, and 8. And why this is 2, 3, 4, 5, 7, and 8? Because they have these strange conditions, like the number of ones in the binary expansion, or you want k to be prime. So these are either prime numbers or powers of 2 smaller than 9. 6 is the only number that is not a power of 2 and not a prime number smaller than 9. Over the reals, this is optimal for 2, 4, 8. And let us pass to something a little different. So these are purely existential results. So we bound the dimension of the areole, and I tell you we can project as long as the areole doesn't fill the whole ambient space. And I mean, people in applications will be not happy with such a theorem. Oh, there exists an interpolation space of dimension this and that. So can we do something about it? Can you do such constructions explicit? And in some sense, yes, because we can parameterize Gorenstein schemes. Not only we know the dimension of the family of Gorenstein schemes in this range, we also know exactly how these Gorenstein schemes look like up to isomorphism. And going through this classification, we can obtain slightly stronger results. For example, we can precisely find points that avoid the areoli. Yes? So how do we avoid the areoli? We need to take every possible Gorenstein scheme supported at a given point, and we need to show that we are not in the linear span of this Gorenstein scheme. And we do it by really considering all possible Gorenstein schemes and providing a linear form vanishing at the Gorenstein scheme, but not vanishing at our given point. And then we perform projections, and these are examples of 4 regular maps that by our theorem, well, they are 4 regular when you restrict to a small ball. Okay. Note that this is, for example, much better than the example I started from R3 to R12. And you can also see that this is much simpler. If you recall that example, there were some 2, 6, it was a very big example. And here it's manageable, I think. But you could still be unhappy because there is this some small analytic ball with unknown factor. So first of all, the radius is unknown. And second of all, well, you need this map that will be a homeomorphism of a ball with a whole affine space, and that's horrible, no? I mean, you don't want such a map. So, can we do something about this? Well, we can do if we relax to C11. So the trick is as follows. The trick is very easy. Consider such a map, and from theory, you know that this is 4 regular in some neighborhood of 0. But this map is very special. Every single monomial is homogeneous with respect to this weight. And now we can use a C-star action to deduce that this map has to be 4 regular. Because if there exist any 4 points, such that their image is not linearly independent, you can scale the points by lambda, and you just scale the image, because every single polynomial is homogeneous, and that would give you a non-vanishing of certain determinant. But you know that this is not true, that when all points are in the small ball, your map is 4 regular. So this tells you that really the whole map must be 4 regular on the whole C3. And just compare this with this result. First of all, this works over complex numbers, and it's always harder to find k-regular maps for complex numbers, because, I mean, if something is linearly independent and defined over reals on C, then of course it's linearly independent on R, but not the other way around. There are many examples of real k-regular maps that are not complex k-regular maps. And also it's much simpler, and also there is a gain on dimension. Okay, so let me conclude in last minutes. So through the study of the Hilbert scheme, we obtain best general bounds for the existence of k-regular maps or interpolating spaces, whichever language you prefer. The results hold both over the real and complex numbers, so we haven't really gone this path of improving over the reals. That sounds very interesting. Best possible results in many cases, up to the theorem that topologists still have to prove. Explicit example of k-regular maps in some cases, polynomial k-regular maps. And, well, by now maybe you can guess that the central conjecture is as follows. That there exists a continuous k-regular map from Cm to Cn if and only if n is greater or equal to m times k minus 1 plus 1. This year there were already 2 proofs of this conjecture on arXiv, both wrong. So the thing is that you can hope to find a really easy k-regular map, and some people do it and then try to prove it, but usually they are wrong. But it doesn't mean that you shouldn't try. I mean, maybe some of you have got a good idea how to produce such k-regular maps. So what are the open problems? Well, topologies don't really provide bounds for polynomial k-regular maps. So I wouldn't recommend fighting with them over arbitrary k-regular maps. I mean, these are really great people knowing their tools very well, working on these subjects for like 50 years. But Can you say something when a polynomial k-regular map exists? That's something I think people haven't considered at all. Although in interpolation theory, some people define k-interpolating spaces only as spaces spanned by polynomials. So that's a little strange that people have not considered this first question. Now, it's even open. We don't know if it's possible that there exists a k-regular map, but there is no polynomial k-regular map. We don't know if such a thing is possible for some fixed n. Then there is a lot of work in topology about skew-regular maps, and our methods have not yet been applied there. I think it's an interesting topic. So what's a skew-regular map? Well, topologists want an even better embedding. Not only that the points are independent, but they want the tangent spaces to be skew, in the sense that they span the tangent together they span a space of highest possible dimension. Well, of course, there is this problem to bound the dimension of the areoli. So I gave you some bounds, but maybe always the areoli, maybe we don't need this assumption that k is less or equal than 9 or m is smaller than 2. Maybe the areolis are of really small dimension. And finally, I already mentioned this. These areolis, they also bound certain, they are also responsible for certain complexity problems. And it would be very interesting to further investigate the connection to fast matrix multiplication. Thank you very much.
Thank you.